All right, well, welcome everyone to this year's first seminar of the BIMR seminar series. I think we have a really nice seminar program for you this year. We're going to be continuing the seminars on Friday afternoon to 2:30, and there are many really great topics, materials with biomolecules, machine learning, nanostructures on surfaces, all kinds of really nice themes throughout the year. And we get to meet in this nicely renovated room. The lights are not yet dimmable. I'm told that they're going to fix that in the evening. It will be 4 days to get everything finalized. But in October, we'll be able to dim the lights in this room. But fortunately, we have a new projector here, so it's bright enough even in this lighting that it's clear to see. With that, it's a great pleasure for me to introduce our seminar speaker for the afternoon, Professor Rachel Evans from the University of Cambridge. Professor Evans did her master's and PhD at Swansea University in Wales. She completed her PhD in 2007, then took up a very prestigious Marie Curie postdoctoral fellowship at Université du Sud, or University of Paris. After that postdoc, she held an FCT research fellowship at the University of Coimbra and the University of Aveiro in Portugal. And in 2009, she began her independent career at Trinity College Dublin as an assistant professor. Stayed at Trinity College until 2017. She rose to the next associate professor. And in 2017, she moved to Cambridge, where she's been ever since. At Cambridge, she is, well, throughout her career, she has led a really exciting research program focused on photovoltaic materials, light harvesting, and lots of interesting applications having to do with energy and light conversion. For her work, she has received a number of awards, including a consolidator grant from the European Research Council, BAME medal, and a Young Researchers Medal from the Royal Society of Chemistry. She is also a fellow of the Royal Society of Chemistry, a fellow of the Institute of Materials, Minerals, and Mining, and a fellow of the Learned Society of Wales. And today she's going to present her work entitled Photon Conversion Materials based on Organic-Inorganic hybrids for photovoltaic and imaging technologies.
Thank you very much for the very kind introduction, and thank you for you all turning up today, Friday afternoon. So it's a great pleasure to be here. My link with McMaster is I've had a collaboration for the last 2 or 3 years with Kalo Saravanamatu, who sadly can't join us this afternoon, but it's a great pleasure to have the opportunity to share some of the work that we've been carrying out in my group. Here we go. First technology issue, Flickr's not working. That's fine, we go old school. Also not working. I have no control of the presentation. Technology. It was working without the Zoom bit. Share. Yeah. There we go. Okay. It's the first one of the year. There's always going to be technical glitches. So, okay. So where was I? So I thought I'd just show you where I'm based, because Canada's a ginormous country and the UK is smaller, but also we're all sort of on top of each other. So Cambridge is just north of London, about an hour on the train. And it's an old university, but we have a sort of a mishmash of really new buildings. So this is the Department of Materials Science and Metallurgy, where I'm based. and that's a new building in 2014. I'm also affiliated with Jesus College, which has been, I'm terrible at history, I think the 1500s maybe. So you have really this eclectic mix of old and new throughout the city. And in my group, we're the photoactive materials group. And basically, we just like materials that like to use light, give out light, do funky things with light. And we work on a variety of different systems, from luminescent solar concentrators, membranes for solar steam generation, liquid crystals, light responsive colloids. So the common theme is all of these things do something or give out light. So today, I'm going to talk to you more about our work on photon converters. And a photon converter is just a fancy way, really, of saying a material that takes light, photons of light, and transforms them into a different energy. So typically, we have a materials system, so we're not dealing with molecules, we're looking at a sort of a solid state or dispersion system, in which we have a luminescent species, or lumiphore, embedded in some sort of host matrix. And the lumiphore is responsible for the photon conversion process. And we can use a variety of different processes. It might be something as simple as photoluminescence or downshifting, where we just absorb light, re-emit at a longer wavelength, and lose some of the energy as heat. But it might be a more complex process whereby we convert, for example, one higher energy photon into two lower energy photons, or the reverse process of upconversion, where we take two low energy photons and convert it to a single photon of higher energy. So in each of these processes, we need to conserve energy, but we're transforming the energy of the photons via a photoluminescence or photophysical process. So we tend to work in organic-inorganic hybrid materials as our host material for our light emitting species. And we are working with, there we go. So we are working with a family of materials known as the ureacyls, and we like hybrid materials because they combine the best of both worlds. We have the flexibility and the processability of organic materials combined with the transparency and the robustness of inorganic materials. And the ureacyls are an example of a class 2 hybrid material. The organic and the inorganic components are covalently bound together. And so we can make these in a really simple process. We're not synthetic chemists at all in the lab, but we can do this chemistry. So we take a silica precursor. So this is just a tetraethyl orthosilicate that's modified with an isocyanate group. And we react this then with any type of off-the-shelf polymer, typically these polyether amines that have functional reactive amine groups. In this case, we've got two. So we can bridge at two sites. And so the isocyanate and the amine react together. We form these urea bridges. So you can see where the urea part of the name comes in. And at this point, so we have our intermediate. And at this point, we can add our light emitting species, our lumiphore. And we can do that in a number of ways. And we'll look at that in a second. To get the final material, then we just do some simple sol gel chemistry. We add an acid catalyst, bit of water, bit of ethanol, and this triggers the hydrolysis and condensation of this silica backbone. So we end up then with our final material, which is like a silica glass that's covalently bound via these polymer chains. And so by varying the nature of this organic backbone, we can tune the material's properties of the system. So for example, if we change the molecular weight or the degree of branching, then we can go from something that's quite glass-like, you can see this sample here, it's cracked, it's fractured because it's really brittle, to something, if we use a single chain polymer that's high molecular weight, to something that's really more flexible and bendy, like a pure organic material. This mechanical tunability means then that we can also vary the processing conditions. And so we can obtain samples by casting in a mold and obtain freestanding monoliths. We could cast our materials on a substrate and obtain a film, or we can even precipitate our ureacyls as nanoparticles into a dispersion medium. So you have different ways of processing the ureacyls in order to develop our photon conversion system. So in order to make our uracil luminescent, I'm going to put a caveat there. I'm going to give a spoiler. Actually, uracils themselves are a bit luminescent, and we'll see that in a few slides' time. But to add the main luminescent species, we can add the lumophore in a few ways. So first of all, for example, we can covalently graft our lumophore. If we modify our lumophore, add on the same tetraethyl orthosilicate groups, for example, to parts of the lumophore, we can selectively graft our lumophore so it sits within the silica domains of our uracil. Alternatively, we might have a really hydrophobic species that prefers to reside in the organic domains. And so in this case, we can get, for example, in this case, this is an example where we use a lumophore that's an aggregation-induced emitter. And we force aggregation within the organic domains. And in this type of luminescent species, that actually switches on the luminescence. So the aggregation promoted by the host matrix switches on the luminescence. We can also, for example, and this is something we're looking at the moment, exploit the urea groups and use interactions via the urea groups as an alternative method to place our lumophores in the matrix. So what I thought I'd do today is give some different examples of how we can use uracil materials as photon converters using different light sources, so indoor light, sunlight, and laser light. We'll look at different photon conversion mechanisms, so photoluminescence, FRET, and TTAUC, and I'll describe those processes when we get there. And then also different material forms, so fibers, freestanding monoliths, or nanoparticle dispersions. So let's start off, first of all, looking at visible light communication using indoor light harvesting. So what then is visible light communication, or Li-Fi? So this is an emerging technology that can be used to transmit data using indoor lighting. So we use intensity modulation of indoor LED lighting. And the advantage of this is it uses existing infrastructure, but also because it's using visible photons, it opens up, there's a lot more bandwidth basically in the visible region than the congested radio wave domain. And so in order to transmit or communicate data, we need a transmitter. In this case, that will be our LED. We need a receiver. This will just be some sort of photodetector. And then we need a digital unit that will encode and decode the signal as we transmit from the light source to the detector. And the great thing about LED lighting is we can modulate the frequency by changing the current, so modulate the intensity by varying the current. And this can be done at really high speeds, so much faster than we can see. We won't be seeing the lights flickering, but it allows really fast data transmission rates, so 500 megabits per second over short distances. So for VLC, one of the challenges is the spectrum of the light source. And actually, we need materials that are going to amplify the blue light component. So we had previously shown that uracils can amplify the photoluminescence quantum yield of blue-emitting dopants. So we put this blue-emitting polyfluorine into our uracils, and we saw two interesting features. The first thing we saw is actually the emission was concentrating at the edges of our materials. And this is because the uracils themselves act as waveguides. This will be important for later applications. The other interesting feature was actually as we increased the lumophore concentration, we actually saw a really big significant increase in the photoluminescence quantum yield. So I hinted at the fact that actually uracils themselves are very weakly luminescent. And this has previously been signed and studied by Luís Carlos's group in Aveiro in Portugal. And it's attributed to a defect emission based on the silica backbone and also a photo-induced proton transfer at the urea groups. Excuse me. But the quantum yield is quite low, 5%. Our conjugated polyelectrolyte is actually quite a weak emitter in solution, so you can only get about 20% in a good solvent. But when we put the two things together, we get this increase in the photoluminescence quantum yield up to 60%. So we have a material that is amplifying the emission of our blue light. And so we thought this could be a useful property if we were trying to implement these in visible light communication. So working with Ruth Ferreira and co-workers at the University of Aveiro in Portugal, we tried to do this. So we took our blue emitting uracil and we processed it in a different form, in the form of fibers. And one of the things we wanted to investigate was not just can we amplify the blue light component, but how does the way we deploy it affect the signal boosting? And that's because there's another problem with visible light communication, interference in the room. So we are all in here interfering with the signal. Okay, light needs to travel and it's going to hit every surface and that will disrupt the signal and result in a bit error rate, which we'll discuss in a few slides' time. So we can implement our amplifier in two ways. We can use this relay node, okay, where we basically put these nodes around the room and they act as hopping off points to transfer the data signal around the room. So you don't have to get all the way to the end at once. You can have a little rest along the way. The other mode we look at is really just using a preamplifier right in front of the photodetector and see if that improves the signal. So what we found was, perhaps unsurprisingly, that the preamplifier mode gave the best result. And we determined this by monitoring the edge-emitted amplified spontaneous emission, which is essentially optical gain that we get from the material. And so you just measure your sample emission at the edge using an excitation stripe of different lengths, and you look at the amplified spontaneous emission, and you get these spectra, and you can just do some data fitting, and this will allow you to get your optical gain. And what we see is for the preamplifier mode, we get an optical gain of around 6 decibels, but in the node, the relay node configuration, it's about 4 decibels. So the next thing that we did, and I say we in the loosest sense, these are always collaborations, but we did some numerical simulations on a standard office. Okay, so this office conforms to EU standards for lighting and office size. Okay, so it's 40 meters squared, 4 LED lights, spaced 2 meters apart. Here is our photodetector. And we've installed relay nodes around the room and also a preamplifier. And then we do some numerical simulations to determine the bit error rate. And this is an important parameter because it measures the number of received bits from a data stream that are altered due to noise. So bouncing off the effect of these signal disruption in the room. So if we don't have any amplifiers, this gray line here represents our baseline bit error rate. So we can only use signal above it. So you can see with this bit here, if we don't have an amplification, we just have quite a small signal. When we install our preamplifiers under each LED, then we get really good signal under the LEDs. But if we look at the 2D transformation, this green line here, you can see that if you're sat in the middle of the room, you've got no internet. So if we add then the relay node, we can see that we can boost the signal in the center of the room. So using the two methods combined, we can amplify the signal by up to 200-fold. So that's using indoor light harvesting. Let's move outside now and look at solar energy harvesting. So we are interested in a technology known as luminescent solar concentrators. And a luminescent solar concentrator, or LSC, just consists of a waveguide slab that's either doped or coated with our lumiphores. And the lumiphores absorb the sunlight, they re-emit it at a longer wavelength just by a normal photoluminescence process, And the emitted photons are then transported via total internal reflection to the edges, where we can install a photovoltaic cell to capture the light. So we are able to harvest light over a really large area and focus it in optically to a smaller area, so we can use smaller and more efficient solar cells. And the reason this is of interest is actually solar cells, solar panels that we're familiar with, they don't really perform well in diffuse light. So in the Northern Hemisphere, this is a picture I still use from Dublin, cloud coverage is an issue, okay? But actually cities are an issue. So if you can only install a solar cell on your rooftop, you're not using all of the walls and the other infrastructure that's available to you. Another issue that LSCs help to, or at least try to alleviate, is converting the solar spectrum. So actually, the grey spectrum here is the spectrum of the sun, and the red area here is sort of the usable energy by a crystalline silicon cell. And so we've got all of these photons that are not being used. These photons here are lost as heat, and these photons down here just can't be absorbed at all. So there's a possibility that LSCs can also convert sunlight into energies that can be used more effectively by solar cells. It's really important to say that this is not a replacement for solar cells. If you have direct sunlight, then clearly putting solar panels is the way to go. But if you want to start to get creative about using solar energy in less conventional ways or utilizing unused surfaces, then this could be a possible solution. So there are lots of things, different technologies that are emerging using LSCs. There's a great review about this. I just highlight this one because it's my collaborator Michael, and he's really the star of the field. He's based in the Netherlands, and they've installed these LSCs as solar noise barriers. So the main functional architectural purpose of the material is to block out the noise from the motorway that's passing by these buildings. But because they're also LSCs, they can capture sunlight and they also generate a little bit of electricity. So this is a type of creative application that we're thinking of. A big challenge with LSCs, even though they've been around for a long time, there's been no standard reporting methodologies in the literature. So we got together a few years back to try and really standardize how people are measuring and reporting LSC performance in the field, so we can actually understand if something is working or not. We're not just trying to get the champion performance, we're trying to see actually are LSCs a feasible technology. So this is the method that we proposed. We have our LSC, we irradiate the top surface with a calibrated light source, normally a solar simulator, and then we capture the edge emitted photons using an integrated sphere that's coupled via fiber optic to a spectrometer. And the figures of merit we're interested in are the ratio of edge emitted photons to absorbed photons, our internal efficiency, and then our ratio of edge emitted photons to incident photons, our external efficiency. So they're the figures of merit we're interested in. So LSCs are quite simple structures. You just got a slab and you've got some lumiphores, but there's actually loads of loss pathways in them, and that's due to different optical loss pathways associated with both the waveguide and the lumiphore. One of the key things that we are interested in overcoming is the problem of reabsorption. So as the photons travel through the plate, they can be reabsorbed by neighboring lumiphores if there's spectral overlap. The other thing that we're looking at is prototyping different architectures. So do we really just have to have rectangular slabs just because that's the way we've always made them? So I'll give you a few examples of that now. So you saw this slide earlier, focusing on the synthesis. Now I'm going to highlight the lumiphore that we used in this case. So this is Lumigen Red. It's a pyrrolene dye, and it's the archetypal dye used in LSCs because it has a really high photoluminescence quantum yield of 90-odd%. But the problem is it has a really small Stokes shift, so a small separation between the absorption and the emission spectrum. You see this strong overlap here, and this is a problem because it leads to reabsorption losses as photons are emitted and transported via total internal reflection through the slab to the edges. And so we expected, what we wanted to do with this study was see if a uracil could behave as a waveguide in an LSC. And that was our primary hope, and yes, it can. But what we do see is that by using Lumigen Red, of course, we get this reabsorption problem, which is concentration dependent. And so as we get to higher concentrations, we get a drop in the total efficiency. So we find 0.005 weight% gave us quite a good efficiency, 9%. And this was really good, actually. We were really surprised. This was actually competitive with anything that was out there in the state of the art. So we thought, yeah, great, uracils are a good waveguide for this application. So in order to overcome the reabsorption question, we wanted to see, could we introduce an effective Stokes shift into the system by exploiting first-order resonance energy transfer? So first-order resonance energy transfer, we're going to have two different lumiphores, our donor and our acceptor. And the donor is going to absorb the sunlight, and the acceptor is going to emit it. So we separate that absorption and that emission process and induce an effective Stokes shift. The requirements for this then are we need to have really efficient spectral overlap. So we need to have strong overlap between the emission spectrum of our donor and the absorption spectrum of our acceptor. So in this case, we use two new lumiphores now that we haven't seen yet. So our donor is this polymer here. It's actually an aggregation-induced emitter. So this donor polymer is not emissive when it's not aggregated. So in a good solvent, the quantum yield's around 0%. But when it aggregates, you switch on the luminescence. And so in a thin film situation, you can get quantum yields up to 70%. Our acceptor is going to be this pyridine dye. And you can see that it's modified at the ends here with these orthoethyl silicate groups. And if we do the acid condensation, the sol-gel reaction with our lumiphore in place, this lumiphore grafts to the silica domains. And this prevents aggregation, which can be an alternative loss mechanism in these systems. So what we wanted to see, first of all, was, did the uracil switch on the luminescence from the donor? Does it cause aggregation-induced emission? And that's exactly what we see. As we increase the concentration of our donor, we get an increase in the emission intensity as the polymer chains are packed closer together, and we increase the emission. And so we get a maximum quantum yield of around 60%, which is not brilliant, but it's acceptable in this case. The problem is, if you're aggregating a polymer within your host material, you're forming aggregates of the size that scatter light. And you can see that then in the samples. So they start off when we've got no polymer in there, they're really transparent. But as we start to get aggregation, they become cloudier and cloudier. And you can see that in the transmittance spectrum. They're really, at this point, unacceptable. So we have this trade-off because we want the luminescence and the aggregation, but we don't want the cloudiness and the light scattering. So we settle with a concentration of around 0.005 weight%. We then optimize our FRET efficiency by tuning the donor to acceptor ratio. And you can see as we increase the acceptor concentration, we essentially get a change in the emission color. But we have a problem because when we get to really high acceptor concentrations, actually we do start to get then reabsorption problems associated with the acceptor because it overlaps with its own emission spectrum. So you get reabsorption issues there. So coincidentally, we found that a 1-to-1 ratio of the donor to acceptor worked best. That was just how it worked out. So what we did is we made big LSCs. And we looked at the internal efficiency of the LSCs. And what we can see is that when we just have the donor, our internal efficiency is about 9%. When we just have the acceptor, it's about 18%. But when we combine the two, we get a small increase of 2%. So it's 20% in total. That's a reasonable increase in terms of LSC efficiency. So we were quite happy with that. I'm just going to deviate slightly away from uracils to tell you something else that we've been doing related to LSCs in terms of varying the shape. We've just looked at rectangular objects so far. And that's because of the way we've been making them and the way most people make LSCs. You cast them in some sort of mold. And so your shape is really limited by the molds that you can buy or construct, okay? But actually 3D printing, we think, is a really good way of prototyping lots of different shapes and seeing, you know, quickly, how does the shape or the geometry affect the performance of the LSCs? And we've been using diffuse deposition modeling, which is an extrusion-based 3D printing process. Because we are making our, we have to make our own filament to do the 3D printing. So that's the first step in our workflow, and that actually proved to be the most challenging. Making fiber, extruding fiber that is within the tolerance limits of your 3D printer is not easy when you haven't done it before. And it's really student dependent. So you've got filaments here prepared by different students and also just let to extrude naturally. Doesn't look like there's a big difference, 2 millimeters to 1.7 millimeters. A 2 millimeter diameter will fail in the print. And the problem is it's not just at one point, so you might be printing for 5 hours and suddenly your fiber is just outside the tolerance limits and your print just fails. This is one of the challenges. But we got there. And so the next thing we started looking at was the shape and the printing pattern. And it's not just the bigger shape that you can change with this extrusion process. The part is printed via a series of lines, okay? So you can actually change your printing pattern. So you can start off by printing in a concentric organization, or you can go back and forth. And we wondered, actually, does that affect the performance of the LSCs? And so what we did then was just come up with lots of different designs. We're just using a simple hobbyist 3D printer, very low cost. And you can see here we've printed different geometric shapes, but hopefully you can see there are different patterns within as well based on these different designs here. One thing that Shomik found out, Shomik was an MPhil student doing with us for a year during COVID, and he's a very smart young chap who's now at MIT doing his PhD. And he realized that actually the G code that we use to talk to the 3D printer can also be integrated into a Monte Carlo ray trace modeling program that is commonly used to predict the efficiency of LSCs. And so what this allows us to do is we can put the exact design, including the line structure of our proposed printed part, model the performance, and then if it looks promising, print the part and see if the actual performance lives up to the predictions. And that's exactly what we find out. So we got really good actual reproducibility between our experimental external photon efficiencies for different shapes and the predicted form. And what we actually find out is that this internal print pattern is actually the really interesting bit. This is the bit that now is, well, you know, it's going off in a completely new rabbit hole, because as science is, the thing that you thought was going to be interesting perhaps isn't, but you unravel and learn new things along the way. So this is why we're going now looking at the internal structure. So just in the final part then, we'll change light source again, and we'll now look at using a laser light source to do some bioimaging. We're going to change our photon conversion process to triplet annihilation up conversion, or TTAUC. I'll explain what that is, and I'm just going to call it TTAUC after that. And now we're looking at uracils as nanoparticles, so a completely different form again. So what is TTAUC? So here's a simple schematic representation. We need to have two sensitizer molecules. They absorb the light. They transform, they convert it via internal non-radiative processes to triplet states. These triplet states then collide with our emitter molecules, which are also in the triplet state, and these annihilate and generate a singlet state of higher energy, which then relaxes. It's perhaps easy to look at the Jablonski diagram to understand this. So what does this look like? So here's our sensitizers, they absorb the light, we get energy relaxation via intersystem crossing to the triplet state. Then we get triplet energy transfer to the triplet state of our emitter on both sides. And then these two triplets annihilate, one relaxes to the ground state and one goes up to the higher energy singlet state, and this then relaxes, giving out light. So the key things about this process are that it's highly oxygen sensitive. There's loads of triplet states here. Ground state oxygen is a triplet, so triplet quenching is a problem. The second issue is we need collisions between our sensitizer and our emitter. Okay, it's diffusion control process. So trying to do this in the solid state is actually really challenging. And I'm going to jump again and just give you a little teaser, because we've managed to do it in the solid state in our urea cells. So here we can see we're shining green laser light into our sample, and we're getting blue emission out in the solid state. There's no oxygen scavenger in there. We haven't removed oxygen at all. The urea cell itself has sufficient barrier properties in order to allow both the to prevent oxygen quenching, but sufficient mobility within the matrix to allow these collisions to take place. But back to bioimaging, why are we interested in TTAUC lifetime imaging? Well, most plants and proteins and animal tissues will show autofluorescence when they're under UV light. And so when you try to use the standard stains for bioimaging, you tend to get emission occurring from the stains and autofluorescence in the same spectral region with the same lifetime. And so it limits the contrast that you can get. You have to be really careful about the stain you're using and know the biology of your sample. So how can TTAUC help? Well, we know we're taking two low energy photons and converting it to a single photon of higher energy. So we can use filters and just look at these anti-Stokes emission rather than the normal lower energy fluorescence. So we're splitting off from the autofluorescence, but also it occurs on a completely different time scale. So it's got to go, because the absorption happens here, and we've got to go through all of these different photophysical processes, the end photon comes out on the millisecond time scale compared to normal fluorescence, which would be on the nanosecond. So you can use temporal gating to split the emission off. So Belong was a postdoc in my group, and he had seen one of our earlier papers where we'd made these uracil nanoparticles, and he thought, well, this would be great for TTAUC. So he prepared our system, he modified the synthesis slightly. So we now have our sensitizer and our emitter. We have our uracil precursor diopties. We have some tween just to act as basically emulsifying agent to stabilize the surface. We throw in an oxygen scavenger to try and reduce the problems of triplet quenching. And so basically you do an emulsion process. We form these droplets, and then we condense the surface, condense the silica structure on the surface to form like a silica coating. And we're able then to get nanoparticles of around 6 to 10 nanometers in size in dispersion. We know that the diopties is important because if we just have all of the other ingredients, here, then actually we get this really cloudy dispersion. So you don't get the nanoparticles forming. When the diopties, our uracil, is present, then we get this clear dispersion of nanoparticles. So first thing we wanted to do was look at the TTAUC properties of our dispersion. We looked at different sensitizer combinations, different emitter combinations. They all work well. They can all be integrated into our uracils. And the key thing here to take from this process is, I guess, here's a dispersion. We're shining our green laser light and we see our blue emission. So we're getting our up conversion from our nanoparticles. As for any TTAUC process, the emission intensity is highly dependent on the power density of your excitation source because it's a multi-photon process. So we can see really that the up conversion quantum yield is really quite low, but it depends very much so on the power density. So we need to get to reasonable power densities before we get a quantum yield of around 1%. This is quite low, but it's certainly adequate to do imaging microscopy with. And so that's what we did. We reached out to Stan Botchway and Sarah Needham at the Central Lasers Facility in the Rutherford Appleton Laboratory. I have to say, all of this was done during COVID, when all the labs was, it was really sort of shuttling samples around and trying to be sort of Belong was very, very good at making things happen. So we did some imaging on cells. We'd never done this before. Sarah's the biologist, and first of all, we had to get the particles into the cells. So there was a lot of optimization of size and so on, but they do go in, and we saw no particle aggregation. We didn't kill the cells, so this was all very positive. And what we used then is a short pass filter to look at the anti-Stokes luminescence. And so our color differences here are just due to differences in lifetime across the cell structure. And so what we see is, first of all, you get quite different levels of different lifetimes across the structures. You can get different distributions depending on the power density of our excitation source. So as I said, the power density is super important because it determines the number of triplet states you have. We've got competition here because we can't exclude oxygen. It's in a living cell. So now we have a competition between TTA-UC, oxygen quenching. But interestingly, this varies across the cell structure. So depending on where the nanoparticles are localized, we get more or less sensitivity to oxygen. And so this is where we had not expected that at all. So this is now where we're starting to look to see, can these actually be sensors as well because of the oxygen sensitivity across the cell structure? Will it also be diffusion dependent, for example? Can we get an idea of changes in microviscosity in the cells? And so on. So with that, then I'd just like to conclude. I hope I've shown you that urea cells are really diverse materials, that they can be adapted and tuned to whatever you really want to do with them. By controlling how we put the lumifer into the material and how we process the material, we can get quite different properties and exploit this in different ways. And so our next steps, we're looking now into this 3D printing of printing urea cells and other polymers to prototype new LSCs. We're looking at combining our LSC concept with some micro-patterning, which we're doing in collaboration with Tala and Catherine. And we're also then, as I gave you a hint, showing, looking at TTA-UC in solid state materials. So I'd just like to thank all the people who did the work. This is the current group, but of course, past members have obviously contributed to all the different projects, and the key people today are highlighted in blue. All of the different collaborators on the projects mentioned today, the funding agencies, and I'd just like to thank you all for your attention. Someone has to be first.
Before I ask the question, I make a silly remark. I've worked for a long time in Europe. I never had a 40 square meter office.
So I actually was thinking of you when I said that, because that's what you should have demanded by putting into EU regulations.
My question, application that you have in the first part.
Yeah.
Where does it come from? Maybe you pay attention to why are you increasing in quantum?
The quantum yield, yeah. So I didn't go into that because it's quite complicated. So basically, the defect sites on the urea cell act as radiative trap sites. They've got a really high radiative probability. So the conjugated polymer harvests loads of light. The energy funnels essentially to these trap sites, it looks like, and then they emit. So you're essentially, it's a fake increase in the quantum yield in that you're absorbing loads and loads more photons than you normally would. And so your output is higher, if that makes sense. Yeah. It would take us a long time to work that out. By the way, I have sight hearing impairment, so I will definitely be wandering over to you. And if you, yeah.
Said that you have the waveguide,
Yeah.
right? So you want to do triplet annihilation.
Yeah.
Now, can you use those to force more collisions?
Within the waveguides, yeah. So one of the one of the challenges is you have to have so we find that the polymer that we use is quite important, and the glass transition temperature of the polymer, right? So you need to have a fairly mobile environment. We don't, they look like solid materials, but within the polymer environment, you get some mobility. So that is the main thing. Using the waveguide process to amplify the signal afterwards, potentially. But yeah, the key thing is getting the sensitizing emitters to find each other in the first place. Yeah.
Do you have these nanoparticles?
Yeah.
You're able to do it.
Yeah.
By shining low wavelength light enough, right?
Correct.
So, do you think there's potential there for nanoflare applications? Nanoflares?
Well, I don't know. What are nanoflares?
Something that you can radiate and then it gives off heat and it can kind of kill surrounding.
Oh, like photothermal effects. Yeah. Potentially, yeah. That could definitely be something worth looking at. Yeah. Yeah. Give you a point, but yeah. I'm going to come to you because this is normal for me, so this is fine.
Very like general question regarding the viruses for the Li-Fi actually.
Yeah, for the Li-Fi, yeah.
Yeah, so like I noticed, for example, because this data is being transmitted in visible.
Yes,
signal,
correct.
right?
Yeah.
So in order to have, for example, access to the data transmission or Wi-Fi, there should be light inside the room.
Yeah, correct. Yeah, you have to have the LED. Yeah. So what happens at night?
Yeah.
Yeah, yeah. It's a great question.
What, according to you, there are like key consideration for the businesses to implement this technology and replace?
Oh, okay. The latter question, I have to say, I'm not sure. I think it will never I can't imagine that it will ever completely replace standard radio wave Wi-Fi, but you could reduce congestion at certain times in the evenings when the lights are on. You could be distributed across Li-Fi and radio wave modes, but in the daytime, then there's a question: can you use sunlight to do it?
Yeah, but one thing that I see as a potential, plus point compared to the Wi-Fi, because it cannot transmit through the walls, and the security, I think, is
yeah, in terms of security, yeah, that's a very good point. Yeah, there you go, and there's your sales pitch. Thank you. Excellent. Yeah, thank you.
This may be just a bit of my life question.
Yeah.
One slide where you see the materials in different shapes.
Oh, yeah.
The inner architecture was what was interesting.
Yeah.
Any insight into what that inner architecture looks like?
So this is about the printing pattern that we use. So if you imagine this printing process, you just are you're printing lines, right? And then you do a single line and you build up into 3 dimensions. But you determine the pattern by which you go into 3 dimensions. So if you go like this to build up your part, or like this, or like this, like this, like this, what we think actually is each line is acting like a little mini fiber optic. And depending on the spacing between each of those lines, you get an air gap. And that will control how well the light is confined within each of those lines. But also you've got scattering interfaces. So there's a balance between having quite a funky pattern inside, which could be interesting because you might minimize reabsorption, but you've got all these scattering and the light has to get out somehow. If it's scattered and it's not going in the right direction. So we are now looking at that. How does that internal pattern affect how efficiently we want the light to go at the edges? So how does that internal pattern affect this? Thank you. Good questions.
Thanks for the very interesting presentation. I was curious if you have any if you have incorporated up conversion sensitizer or emitters into monolithic systems, or whether they require a specific environment to function as an up conversion system that might only be possible in an empty morphology.
So the video I showed, that is exactly that. That's incorporating the solid state, the TTA-UC lumiphores within the uracil system. This one here. So that is a solid, that's about 3 centimeters by 3 centimeters, I would imagine, about 1 millimeter thick. It's obviously not going to play now because I've gone backwards, but but what we saw there is exactly that. Yeah, that we are looking at stuff like functionalizing the lumiphores now so that they sit in certain parts of the uracil and seeing if that controls the TTA-UC efficiency. But actually, these are up there with the best solid state TTA-UC system. But again, just trying something and it works. Sometimes you get lucky.
Rachel, I have a question about the mechanical properties. So
Yeah.
you showed some that seem like they were flexible.
Very, yeah.
Some draw fibers.
Yeah.
So what controls that, and how flexible do you make these things? Are they stretchable, and how does that impact the?
So the stretchable thing is something, you know, and you have that project that you're just like, I really like, everyone always asks about this, and it's like, I should really look at that sometime because they can be really, really flexible if depending on the polymer backbone you use. So the scheme I showed used a linear polymer, right? You had an amine at either end of the chain, but you can buy different versions of this. So tri-branched, 4-branched, with multi-arms like this, right? And depending on the relative molecular weight of your organic bit, now your grass, if you got silica nodes at each of the end of those things, your ratio of organic to inorganic is actually controlled by that branching and the molecular weight. So if you have a tri-branch system or 4-branch system, they tend to be really glassy and hard and brittle. We tend to use those as much because they're not as nice to work with. But if you have like a long, so these are not long polymers. They're molecular. I mean, you can't read. They're sold as polymers. You know, the molecular weight's about 1,000, so it's not very high. And so you could envisage if you went much higher, actually. So we're doing some mixed, like copolymers with methacrylates and so on now to see actually how that really affects how polymer-like we can make these things. But they can just be really, really rollable and maintain their mechanical properties. But the alignment thing I think is super interesting on the, like, if you're pulling it stretch in one direction, how does that change? Yeah.
Really good.
Thank you.
So if you had also a slide where you show some syntheses using the soil gel.
Yep.
So if you had it fairly mild with the right glass transition
Yep.
temperature that you like, couldn't you just functionalize the surface to use the kind of properties that you'd be interested in?
To change this, sorry, I'm not quite sure. I
Couldn't you just functionalize the surface if you already had it fairly mild that you were happy with
Yeah.
glass transition temperature, instead of synthesizing from using the soil gel process
Yeah.
like you described?
Mm.
Couldn't you just add functional groups?
So just take the polymer.
Yeah.
So what? So the silica bit adds the toughness that we're looking for, but actually it adds the refractive index change that we need. So the polymer alone doesn't quite give us the refractive index that we need for them to be really working well as waveguides. So that's kind of, yeah. I think there were a few from students, so yeah. Well, I'm going to come to you.
I'm not sure if the internal pattern is desirable for your application, but have you considered removing them by possibly like annealing your printed material?
Yeah, that could, or even so at this point we actually think it's beneficial, but we had considered transitioning to like a photopolymerization 3D printing method like SLA or annealing or something like that. At the minute, it's a good question. At the minute, we're trying to understand why are we getting such differences, and we actually do get an enhancement, but it is not immediately obvious how, what is good and what is bad. We definitely get a lot of bad ones as well. So yeah, that's a great idea. And yeah. In the nanoparticles, yeah.
Can I ask this diagram here, do you have localized heating when you're
So in this one, no, we can, yeah, no, there might be heating on the edges, but the emission is observed all the way through the sample. So we don't think that's a huge problem.
So there shouldn't be any TADF?
No, we're not expecting TADF. Yeah. No, good question. Yeah. Oh, yeah. That's what we do, exactly that. So yeah, so we've looked at all the way through, but also sort of boom, 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 boom. Yeah. And that's what makes it so complicated, because actually you've got an infinite number of variables. Yeah. Yeah. So we're now trying to simplify the problem and then recomplicate it again. Yeah. Thanks, good question.
Okay. I think with that, we can stop the question period. Thank you.